I remembered to record today, so hope we don't have any crashes this time. All right, so we've come a long way, and now we're at the end. So let's go through our last section of the review. All right, some of you are just seeing this now. So we'll go through the last section of the final exam review. But before I start that, a couple reminders. I'll be around all week, so if you need to come see me in my office, you're not really that restricted on time. I'll be there most of the time. And then for the final exam, scheduling is a lot tighter because CASA has to fit in several exams in the period of a couple weeks or so. So there's space is a lot more tight. So what I'm trying to say is make sure you're on time to your exam and don't miss it, because it'll be much more difficult to reschedule for the final. I wouldn't say it's impossible, but it's not something you want to have to deal with during final exams, is having to reschedule your CASA time slot. So please be on time. Please go to the right location, which is still CVB, the same location we've had all our exams at. But that's going to be a little bit more of an issue if you miss your final exam, because there's not as many spots available. All right, and then before I start with the final exam review, I want to go over one topic that I sort of skimmed over, didn't really cover much at all in the confusion of class cancellations and other things happening. I sort of left it out. But there's a roughly 10% chance you'll get a question about this on your final, so I just want to make sure we're clear on it. It's nothing too difficult or complicated, but we've been talking about how the different bonding arrangements in solids in different condensed phases affect their properties. So we've talked about metallic bonding, we've talked about covalent bonding, and we talked a lot about ionic bonding, but didn't really wrap it up and talk about the properties that result from ionic bonding. So there's the three things we're interested in are the mechanical properties, the conductivity, specifically the electrical conductivity, and the melting and boiling points. All right, so if we think about ionic compounds, we are certainly familiar with some in our everyday lives, and they tend to be hard and brittle. All right, so we talked about how metallic compounds are malleable because you have that loose sea of electrons. The atoms can move around within those loosely held electrons, and you get good malleability, which is the ability to bend or distort the structure. Not so much with ionic compounds. We know that if we take a big piece of rock salt and try to bend it, that doesn't quite happen. It just shatters if we put enough force on it. So they're hard and brittle. And why is this from the structural standpoint? We know that in ionic compounds, the ions are sort of locked in place because they have these strong interactions with each other in the crystal structure. So you can't really slide them around each other. So in metallic compounds, we said we're able to slide the atoms around, and that gives them their malleability. We're able to maintain that metallic bonding. But in ionic compounds, you're not really able to do this, and that's why they're sort of brittle. If they want to stay in place, and if you put enough force on them, they just break off as pieces. Okay, the other one we want to talk about is electrical conductivity. Ionic compounds are insulating in the solid phase, so they're electronically insulating when they're solids. But if we're able to liquefy an ionic compound, which is not a common scenario, but if we go to high enough temperature and liquefy them, they'll conduct in that phase. So the liquid, or what we call the molten phase. So they will conduct electricity in this situation, but not as solids, which is their more typical form. Now, why is this? In the solid phase in particular, the charges are very localized. So we talked about in conductors and semiconductors, you need to have mobile electrons that can move between orbitals at different energy levels. In a solid ionic compound, the electrons are very localized on the individual negatively charged ions. So the charges are, as we talked about in ionic compounds, you have discrete positive and negative charges that are localized, and they're not able to really move around the structure. So because of this localized nature, there is no electron mobility. And to introduce a term to use a term that we introduced last week, ionic compounds have large band gaps. And that's true of all insulating compounds. And if you think about why this is, you have the filled orbitals, which are localized on the nonmetal. Those have those take all the extra electrons and make the anions. And then the metallic orbitals, which are empty, are going to be much higher in energy. So you have a large gap between your filled and empty orbitals, you have localized charges, you don't have these immobile electrons that you need for conductivity. And then finally, the melting and boiling points for ionic compounds are very high. And this one's probably the easiest to rationalize because, as we've talked about in many different contexts, ionic compounds have very strong interactions between the positive and negative ions. If you're going to melt, or especially if you're going to boil the compound, you need to break up those interactions. That's very difficult to do. You have to put a lot of energy in. So these strong attractions give rise to very high melting and boiling point. All right, so that's a little bit of detail about the ionic structure. We don't really need to worry about it in any more detail than that. And then I think to help summarize all of this stuff, to try to tie it all together, here's another table for you that just lists the key properties that are related to bonding. So we've talked about 3 types of bonding in this course, ionic, covalent, and metallic most recently. And we've also touched on how different properties of these substances relate to that bonding. So let's just quickly wrap that up here. So we just finished ionic compounds, so we're just going to essentially copy over what we had from the previous. So they're hard and brittle. Their melting points and boiling points are very high. And their conductivity, their insulators, in the solid phase, and their conductors, if you do go to a high enough temperature to liquefy them, they will conduct electricity in that phase. But normally they're in the solid phase, they're insulators. We talked about covalent compounds, and covalent compounds are the ones where the properties really depend on the type of covalent compound it is, because there's 2 basic types. We talked about the network solids, which are those that have covalent bonds extending in all directions, and we talked about molecular compounds, which are just discrete molecules that would be held together by intermolecular forces in the solid phase. So the properties really depend on the type of compound it is. So for the network solids, of which diamond is a very typical example, those tend to be hard. All right, so diamonds, we know they're one of the hardest substances in the world, and that's because of this strong network covalent arrangement. But they could also be soft. Covalent compounds can be soft if they're molecular compounds. So molecular compounds are typically held together by very weak forces, and these give rise to some very soft substances. So again, the exact type of bonding or the exact type of structure they form will really affect the properties. And the same is true of the melting points and the boiling points. They can be either high or low. So if you have a network compound which has strong covalent bonds extending in all directions, they're going to tend to have very high melting points. You have to put a lot of energy in to break those bonds and melt the substance to release the atoms from each other. But if it's a molecular compound, they have low melting points because, again, there's weak forces holding them together. So it really depends in these types of compounds. Boiling point follows the same trend always, so we don't have to really talk about that separately. So a lot of our molecular compounds that we're familiar with are liquids or gases at room temperature because they have weak forces. Did I screw something up probably? Yeah, I did. It's that time of day for me to screw something up. All right. These would be molecular, sorry. Okay, so the molecular solids tend to have low melting and boiling points. And then conductivity, we saw that most covalent compounds, whether they're network or molecular, are insulators. So very few of them are conductors. However, we saw that there's some exceptions to this. Graphite is a conductor because of the delocalized pi electrons. And then we should be aware that silicon and germanium, which are network elemental solids, so very similar to carbon in structure, those are semiconductors. So we talked about semiconductors a little bit as well. And these are the 2 most common elements that are classified as semiconductors. So these network covalent compounds have band gaps, gaps between the filled and unfilled orbitals. Those can vary depending on what element it is. They tend to be very large, but in some cases they're moderate gaps, and they do exhibit semiconducting behavior. All right, and then finally the metallic compounds. We saw that from a mechanical standpoint they're malleable. As we talked about, that means they can be bent and distorted. Melting points, if we're using very qualitative terminology, these would be moderate. So the metallic bonding doesn't hold the atoms in place nearly as rigidly as ionic bonding does. That relates to the mechanical properties as well. And because of this, you can melt them typically at not too high of temperatures. It's still, most metals are still solid at room temperature, but you don't have to usually go to very high temperatures to melt them in a lot of cases. But the boiling points tend to be high because in this case you have to break all of those attractions between the nuclei and the electron C. And then finally, conductivity. All metals are good conductors. That's one of their key properties, and this is both true of solid and liquid metal. So in both condensed phases, metallic compounds are very good conductors of electricity. All right, so that summarizes the key properties of all these compounds, and now we have to sort of just jump in and get through the rest of these review problems before we run out of time. Most of these problems at the end especially are conceptual, so they shouldn't take as long to go through, but let's get started on these. All right, so the first one deals with combustion enthalpies. So here we're talking about benzoic acid, which has a combustion enthalpy of minus 3,227 kilojoules per mole. If we burn 5.25 grams of this compound in a bomb calorimeter containing 1,100 milliliters of water and the temperature change is 24.9 Celsius, what is the heat capacity of the calorimeter by itself in joules per degree Celsius? So one thing that seemed to be a little bit of a difficulty on the previous exam, among other things, was that when you're talking about calorimetry problems, there's really two terms involved. So you do a chemical reaction in a calorimeter, and the heat that's either evolved by that chemical reaction or that goes into that chemical reaction is going to be either absorbed or supplied by the calorimeter. And the calorimeter really includes two pieces. So if we're calculating the heat absorbed by the calorimeter, this is a combustion reaction, so it's going to be heating up. We have water in the calorimeter. Very often we're going to tell you how much water there is, and that's going to be the MC delta T term. But then we also have the calorimeter itself, all the other material that makes up the calorimeter. And if you did this in the lab, it's probably like a coffee cup or a thermos, but they can be obviously more elaborate than that. So whatever other materials make up your calorimeter are also going to absorb some of the heat. So you have this overall heat capacity of the calorimeter by itself times delta T. There's no mass term associated with it. We don't have to we don't measure the mass of the calorimeter. It's made up of a bunch of different substances usually. So we just report an overall heat capacity. And then we multiply that by delta T. So in this problem, that's what we're solving for here, is our unknown heat capacity. So to be able to do this, we have to figure out the heat that's absorbed by our calorimeter, remembering that the heat absorbed by the calorimeter is equal and opposite to the heat involved with the reaction. So Q cal is equal to minus Q for the reaction. So if we can figure out what the heat of our reaction is, then we just take the negative sign, or the negative of that, to get the heat for the calorimeter. So in this problem, we're given enough information to find the heat of our reaction because we know the enthalpy of combustion for this substance and we know how much of the substance we're using. But remember that enthalpy of combustion, minus 3,227, that refers to burning 1 mole of substance, but in this calorimetry problem, we're only burning 5.25 grams, which is much less than a mole. So how much heat is actually involved, we have to figure that out. So the heat for our reaction is, we take 5.25 grams of benzoic acid, and then our combustion enthalpy is given to us in kilojoules per mole. That's the most typical arrangement, but sometimes it'll be kilojoules per gram, which makes your life a little bit easier. But here we have a kilojoules per mole combustion enthalpy, so we convert this mass into moles first. Using the molar mass that we're given, 122.1. So that converts into moles of benzoic acid, and we know from the combustion enthalpy that the heat of the reaction is going to be minus 3,227 kilojoules for every mole of benzoic acid that burns. So this is minus 139 kilojoules, or if we want to convert to joules, which we'll see we have to do, minus 139,000. Now the reason we're converting to joules is because we eventually want our heat capacity in joules per degree Celsius, so we're going to need that value in joules for the equation that we wrote at the top to work out. So now that we have that value, we know that the heat for our calorimeter is just the opposite or the negative of that number. So that means our calorimeter is absorbing 139,000 joules of heat. Some portion of that is going into water. That's the MC delta T term. So we have the mass of water needs to be in grams. We have 1,100 milliliters, which is 1,100 grams of water. The heat capacity of water, I don't think I gave it to you here. It's the one we should be familiar with, 4.18. And then delta T, we're told, is 24.9 Celsius. It should be a positive number because this is a combustion reaction, so we're going to be heating up the surroundings. And then we have our unknown heat capacity for our calorimeter times the same delta T. So that's the other important point. Delta T is the same. You're reaching a thermal equilibrium where the calorimeter and the water that's in the calorimeter end up at the same temperature. So our only unknown here is the heat capacity of the calorimeter. Everything else was either given to us explicitly or we had to solve for the heat using this information above. So once we solve for the heat capacity of the calorimeter in joules per gram, if we use all these numbers that I've given you here, 979.9 joules per degree Celsius, not per gram. And that's the number we would put into Blackboard. So in these calorimetry problems, this general equation up here is always going to be true. You have, when you're doing a chemical reaction in a calorimeter, the heat's going to be, there's going to be a heat term associated with the water and a heat term associated with the calorimeter itself. Sometimes we don't give you both pieces of information. So depending on what we give you in the problem, you might ignore one of these two terms and assume that all of the heat is absorbed by the water, or all the heat is just absorbed by the calorimeter, which might include the water. But if we give you both the mass of the water and the heat capacity, or in this case we're asking you to find the heat capacity, you need to include both of those terms in the calculation. So the heat is absorbed by both of those things. Okay, questions on that one? All right, so all this stuff is pretty recent, so hopefully it's not too foreign at the moment. Okay, so for this reaction we're going to calculate delta H. We have methane plus ammonia going to hydrocyanic acid and hydrogen H2. And we have three reactions. So this is a Hess's law problem where we're going to add together multiple chemical reactions to get our overall reaction and our overall enthalpy. All right, so if we just go through one reaction at a time. So our overall reaction is given up here, and we have three equations that we're going to add together. So if we look at the first reaction number 1 here, this has ammonia as a product, but our overall reaction needs to have ammonia as a reactant. Okay, so we're going to flip this first reaction, and we're also going to multiply it by 1/2 so that this coefficient of 2 here in front of ammonia becomes a 1. So ammonia only appears in this reaction here, and so that way we can just know what to do with that first reaction. So we're going to take minus 1/2 times the first equation, which then modifies it to read NH3 going to 1/2 N2 plus 3/2 H2. And that means the delta H for this modified reaction is minus 1/2 times the first delta H, which comes out to 45.9. Okay, so we wanted to have NH3 on the reactant side, so we take this first reaction, we flip it over to make NH3 on the reactant side. That puts a negative sign in front of delta H, but we also have to multiply the coefficients by 1/2 because we want just a coefficient of 1 in front of NH3. This one has 2. So by doing that combined operation, we multiply delta H by minus 1/2. So it's a combined operation there. We do the same thing. So for equation 2 has methane as a product, CH4. What we want it on the reactant side for our overall reaction, so we're going to flip equation 2, but this time we don't need to modify the coefficients because this already has a coefficient of 1 in front of CH4. So if we take the inverse of the second chemical equation here, we get CH4 going to carbon and 2 H2s. We'll just leave out the phases of matter. Doesn't really matter. They're all. And then delta H for this modified equation 2 is going to be just the inverse of the negative of the second delta H, 74.9 kilojoules. So we flip the reaction. That just flips the sign of delta H but doesn't do anything to its magnitude. And then finally for the third one here, this third equation has HCN as a product, but it has a 2 in front of it. So if we take half of this third equation, that'll give us 1 HCN as a product, which is what we want, in our overall reaction. So we're just going to do 1/2 times the third. So we get 1/2 H2 plus carbon plus 1/2 N2 goes to HCN. So the delta H for this is just going to be 1/2 times the third delta H. All we did was multiply the coefficients by 1/2. So we get 135.2 kilojoules. Alright, so those are the three modified equations and the modified delta H. Now we also notice that our overall reaction has H2 in it, but H2 appears in all three of our equations down here, 1, 2, and 3. So it would be sort of a foolhardy mission to try to balance H2 using these reactions, so we don't know what combination of these three reactions is going to give us the correct amount of H2 on the product side. But we also have the rest of the three reactions and products, CH4, NH3, HCN, they only appear once down here, so we can use that information to help us decide whether we flip or multiply the coefficients or some combination of those two. So when we add these together, our CH4 carries through, which is, it doesn't cancel out. NH3 also. And then we have over here 1/2 H2. So that'll cancel out with this partially over here. So then we'll have 3 H2 on the product side. So that H2 cancels out with what's on the product side. We have this carbon here cancels out, and this 1/2 N2 cancels out up here. So we're left with those two reactants, and then on the product side we just have HCN, and in that we have 2 H2s plus 1 H2 is 3 H2s. We can verify that the reactions add up properly, and then the delta H is just going to be the sum of these three values here, the modified delta H's that we got when we rearrange the reactions, and we get 256.0 kilojoules. Okay. All right. So Hess's law, we saw a lot of problems like that on the third exam, at least 2, I think, and there'll probably be 1 on the final as well. Okay. Any questions on that? All right. Moving on then. Tetraphosphorus pentoxide reacts with water to form phosphoric acid, as shown below. This one seems a little bit out of place. I forget why I put this in here, but it's a stoichiometry problem. We just want to know how many moles of water are required to react with 5.23 times 10 to the 24th molecules of P4O10. All right, so in this problem we have the balanced reaction, and we're trying to find moles of water. We have molecules of P4O10. So this is a pretty straightforward stoichiometry. It's just we have to use Avogadro's number to first convert into moles. So we're told that we have 5.23 times 10 to the 24th molecules of P4O10. Stoichiometry revolves around moles, so if we want to convert this into moles, we have to use Avogadro's number. So 1 mole is going to have 6.02 times 10 to the 23rd molecules. And then we're going to use the coefficients from the balanced reaction. We're trying to figure out how many moles of water react with that much P4O10. So if we go to the balanced reaction, we have a coefficient of 6 in front of water, coefficient of 1 in front of P4O10. So that means 6 moles of water are required for every 1 mole of P4O10. And we stop there because we're asked for moles of water. We don't need to go any further into mass or anything else. So it's going to be 5.21 moles of water. Or sorry, 52.1. Lost my decimal place. There we go. And that matches up with choice D. Alright, so this one was a little bit out of place. I'm not sure why I put it here, but it's still a good problem for us to review. A stoichiometry problem, but using Avogadro's number at first to convert between moles and number of entities or molecules in this case. All right, questions on that? Okay, so number 28, back to gas laws. We have a container of gas with a movable piston, has a volume of 123 milliliters when the pressure is 562 torr and the temperature is 25 Celsius. What will be the volume if the pressure is lowered to 253 torr and the temperature is raised to 97 Celsius? So here we have three variables we're considering: pressure, volume, temperature. It's a closed container, so we're assuming that the number of moles is constant. We're also not told anything about the number of moles. But if we start with PV equals nRT, n is going to be the only of the variables that's constant. So that means when we rearrange it, PV over T is going to be equal to nR, which is a constant. So that means we can write a combined gas law. This doesn't really refer to a specific one, but P1 V1 over T1 equals P2 V2 over T2. This is a very common one we use. It comes, again, directly from PV equals nRT, or we can derive it from that. This is a very common one, though, because if you have a set amount of gas, some number of moles of gas, and you're changing some combination of pressure, volume, and temperature, you're going to have this relationship between those three parameters. So in this case, we're looking for the final volume, so we'll call that V2, and we just solve for V2, which is going to be P1 V1 times T2 over T1 P2. All right, so make sure we do the algebra right. We get that relationship there, and now we can just start putting things in. So our initial pressure is 562 torr. Now, as I reminded you before, if we have this type of problem here where we've dropped out our universal gas constant as a constant, so we don't have R in this equation, so we can use whatever units we want for pressure and volume specifically. So as long as the two pressures, P1 and P2, are in the same units, it's just a ratio of those two, so they don't have to change them necessarily. So they're given to us in torr, so let's just keep them like that. So we have 562 torr. The initial volume, V1, is 123 milliliters. Again, if we're looking for the volume in milliliters, we read the problem closely, that's the unit we want, so we'll just keep that volume unit, milliliters. It doesn't matter again for this. So 123 milliliters. And then T2 is the second temperature, which is 97 Celsius. We need to convert that into Kelvin. So we add 273 to that to get it in Kelvin. This is the one unit that's not negotiable in any gas law problem is temperature. It has to be in Kelvin. The initial temperature is 25 Celsius, which, if we convert that into Kelvin, is 298. And then our second pressure, P2, we said the pressure is lowered to 253 torr. All right, so we have a sort of a combined change in pressure and temperature. We calculate this out to find the final volume, and we get 339 milliliters. Okay, so starting with the ideal gas law, we can derive relationships between any two or three of these variables, and then we can set the initial and final set of conditions equal to each other, solve for what we're looking for. All right, any questions on that one? Okay. All right, this is one of those conceptual problems that we always seem to have a little bit of trouble with. Which of the following plots for an ideal gas would yield a straight line with a positive slope, assuming all of the variables are constant? So we're talking about pressure versus volume, pressure versus temperature, pressure versus 1 over volume, or some combination of those three. So when we're approaching problems like this, of course it all starts and ends with the ideal gas law. So we start with PV equals nRT, and then we're going to just separate the two variables we're interested in. So we're going to call one of them y, the other x. Usually when we say, P versus V, oh no, don't go away. I lost the right projector, hang on. All right, good. Okay, we're back. Okay, so PV equals nRT. Let me make sure the video's okay, because if you change the resolution on these, sometimes it gets screwed up. Alright, I think we're okay. Anyway, back to this. Okay, so then we're going to separate the variables. So we want to put the two variables that we're comparing just on opposite sides of the equation to derive a relationship between those that we can then plot as a y versus x type of graph. So for choice A here, we're doing pressure versus volume. So we're going to take PV equals nRT, we're going to move volume over to the other side. We get that P is equal to nRT over V, which is equal to some constant, which I'll call m to relate it to the slope of a line, over V. However, if we're plotting, a y-x graph where we have pressure and volume here, this rearrangement gives us, y is equal to some constant divided by x, so that's not a linear plot. So if we have volume here is in the denominator. If we're plotting V on the x-axis, we have 1 over V is our function here. This is going to be sort of an asymptotic graph like that. So this first one would not be linear. If we look at choice B, pressure versus temperature, we move everything over, so we have pressure on the y-axis. All these have pressure on the y-axis that we're considering. It's going to be nR over V times the temperature, which is equal to some constant times the temperature. All right, in this one we have y equals m times x, so that's going to be a pretty simple straight line. We have pressure and temperature, so this one will be linear. And then finally, if we do choice C up here, pressure versus 1 over volume, pressure is equal to nRT times 1 over V, which is equal to some constant times 1 over V. But if this whole thing is our x variable, so we have pressure, we have 1 over the volume this time on the x-axis, this will give us a straight line. Because here we're not just plotting volume as our x variable, we're plotting 1 over the volume, the inverse of the volume. So if we replace that whole thing with what we call x, that's going to give us a straight line also. So both B and C will give us linear plots. And another key point that I've made before is when you rearrange the ideal gas law to derive linear relationships, you're never going to have a non-zero intercept, provided your temperature is in the absolute scale of Kelvin. So all of your intercepts, you only have one term on each side of the equation, so you're never going to have a y-intercept that would show up in these equations. Okay, so those might come up a little bit as well. We'll learn how to sort of rearrange those equations, and then it goes back to just simple y equals x or y equals 1 over x types of plots. Okay, questions on that? Yeah. So A is not linear because this equation, P is equal to nRT over V, is sort of the same as y is equal to some constant divided by x. So it's x to the minus 1 power. So volume is, it's inversely related, so you don't get a linear relationship. You only get a linear relationship when it's y equals something times x, not something divided by x. Now the reason C is linear is because we're taking this whole 1 over V and making that our x-axis. So now this whole quantity here is our x variable, so it's still some constant times x. So that's sort of the difference between those two, and why one is linear and one is not. All right, good question though. Anything else? All right, on to number 30. Make sure we have enough time to get through all these. All right, now we're on to the conceptual questions dealing with phase changes and intermolecular forces and all those good things. In which of the following elements in their standard states, so that's the key word here, standard states, are the atoms held together in the solid state by London dispersion forces? So for all of these, we need to figure out what is the standard state of the element, so figure out which ones are solids and then which ones would then be held together primarily by London dispersion forces. So if we go through all of these, choice A, carbon, the standard state for carbon we talked about is graphite. Okay? And this is one of our examples of a network covalent solid. So in network covalent solids, the individual atoms are held together by covalent bonds. Now there are also London dispersion forces in these, but that's not the most important or not the exclusive intermolecular force. So there's, as we talked about in graphite, there's layers of atoms. All those atoms are covalently bonded to each other, and then the individual layers have sort of London dispersion forces that are holding them together. But the atoms are held in place by covalent bonds, so that's going to be the strongest force that's holding them together. So A is not going to work. If we look at choice B, sodium is a metallic element, so the atoms are going to be held together by a metallic bond, so we don't have London dispersion forces. Is certainly not going to be the most important. This is probably a poorly worded question. It should have been held together exclusively by London dispersion forces. So So all of them will have London dispersion forces between the atoms, but we're talking about the one where the London dispersion forces is the only force. I should have been more clear about that. This is not copied from the exam, so you don't have a confusing one like this on the exam, don't worry. And then choice C, so the standard state of bromine is Br2. So this is a compound that would only exhibit London dispersion forces. However, the standard state for Br2 is what phase of matter? I've heard a lot of gas. It's liquid, thank you. Okay, so it is a liquid. Okay, so Br2 is one of the only two elements that's a liquid, Br2 and mercury. So Br2 is a liquid under standard state, so it's not going to be held together in the solid state by London dispersion forces. It is held together in the liquid state, so that was sort of the key to that one, is remembering our standard states. And then for choice D, gold is also metallic. So again, it has those metallic bonds holding the atoms in place. Finally, E, sulfur. The standard state for sulfur is S8, which is in fact a solid. And this is a molecular solid. It has molecules of S8, and those molecules are going to be held together by London dispersion forces. So it's a molecular solid. It's of course nonpolar because it's just one type of atom, and it's going to have London dispersion forces as the only intermolecular force. Okay, so that would be choice E. All right, moving on to 31. Which of the following statements is false? We have three statements here, mostly dealing with silicon and comparisons to other elements as well. Okay, so number one here, silicon has a larger band gap than aluminum. Okay, so remember that band gap is the distance between the filled and the unfilled molecular orbitals. So when we're talking about extended solids here, you have energy going up, you're going to have some filled molecular orbitals where all the electrons reside, and then you're going to have some empty molecular orbitals. And we draw these as bands because you don't have discrete orbitals. You have a lot of orbitals that are all really close in energy, so they form sort of a continuous band of orbitals that are all filled, and these are going to be then another continuous band that are unfilled. And then the band gap then is going to be the distance between them. So how far apart those two are in energy. And that's going to determine the conductivity properties. For something that's a conductor, the two levels are pretty much right on top of each other, so there's no band gap. For insulators, these two are far apart, so the electrons can't move into the unoccupied positions. And then finally, for semiconductors, you're sort of somewhere in between. Okay, so if we look at the two elements we're comparing in number one, silicon and aluminum, as we talked about earlier, silicon is one of our classic examples of a semiconductor. So that means it has an intermediate band gap. It's somewhere in between an insulator and a conductor, semiconductor. But then aluminum, what kind of element is that? Aluminum is a metal. Okay, so metals have smaller band gaps than semiconductors, so this first one here is going to be true because silicon would be larger than aluminum. So a semiconductor versus a conductor, the semiconductor will have the larger band gap, so this first one is true. So we're looking for the false statement, so that one's not going to be one of our choices. Number two here, silicon doped with phosphorus would be a p-type semiconductor. So remember, for semiconductors, there's two types of dopings we can do. One of them is going to be p-type, one of them is going to be n-type. So you have to know the difference between them. So for a p-type semiconductor, we're going to be putting in an element that has less valence electrons. So if we go to the periodic table, which I'll have to pull up here. So on the periodic table, we have silicon is over here in group 4, so it has 4 valence electrons. And we're doping it with phosphorus, which is in group 5, so it has 5 valence electrons. So in phosphorus-doped silicon, we have 4 valence electrons in silicon, and then our dopant has 5. So if we're doping in extra valence electrons, this would be an n-type. So this one is going to be false, okay, because that type of doping would be n-type doping. We're putting in extra valence electrons, so know the difference between p-type and n-type. And then finally, choice 3 here, the conductivity of silicon increases with temperature. So this one I don't remember if I mentioned it in class or not, but for semiconductors, this is one of their key properties. So when you have a semiconductor, the conductivity goes up when the temperature goes up. All right, so there's that direct relationship. And that's because you have that intermediate band gap. If you increase the temperature, you're going to give the electrons more energy, and more of them are going to be able to cross this band gap. For conductors, it's the opposite. The conductivity, as you may have learned in physics, for a metal conductor is going to go down as you increase the temperature, and that relates to the sort of the ordering of the electrons in the structure. Not something we really need to talk about in detail. But semiconductors and conductors, that's sort of another distinction between them is the behavior of the conductivity with temperature. For semiconductors, conductivity goes up when you raise the temperature. For conductors, it's the opposite. Okay, so semiconductors, that one would be true then as well. So the only false statement, which is what we're looking for, is number 2 here, which corresponds to choice B out of our multiple choice answers. Okay, questions on those concepts? Yeah. Why is number 2 false? Because silicon doped with phosphorus would be an N-type semiconductor. So when you dope a semiconductor, you can put something in that has either slightly less, has less valence electrons or more valence electrons. If what you're putting in has less valence electrons, that's P-type. If you're putting something in with more valence electrons, that's N-type. Phosphorus is to the right of silicon on the periodic table, so it has one more valence electron. So that material will be called an N-type conductor. So it's just sort of the opposite situation. Okay. All right, moving on, number 32. What is the empirical formula of a compound containing A on the corners of a cubic lattice, B on the edges, and C in the center? So one of the main things we have to be able to do with cubic structures, so we saw some homework problems this week, or if you've done the homework, about relationships between the atomic radius and the cell length, some of those geometry things. We're not going to have that on the final exam, but it is something good to go through on the homework just to really familiarize yourself with the structures. But one thing you're going to have to do for sure is know how to count the different positions, the corners, the edges, the faces, and the centers. So here we have A is on the corners of a cubic lattice. Okay, so there's corners, there's 8 corners, and then each of them is shared by 8 unit cells, so that each count is an eighth. So there's going to be in total 1 atom of A in our empirical formula. For B, we have B is on the edges of a cubic lattice, so there are 12 edges in a cube, and then each of those is going to be shared by 4 adjacent unit cells. So there's going to be 3 B's if they're just on the edges. And then C is in the center, so there's only 1 center position, and it counts as a full atom because it's not shared between unit cells. So we have 1 C. So that means our empirical formula is A, B3, C, and we can't reduce this down any more than that. Okay, so when you're determining empirical formulas for compounds, whether they're real compounds or hypothetical compounds that are in one of these cubic structures, if you know how to count the different positions, so that includes all of the positions along the edges and the faces of the cube, as well as we talked a little bit about the tetrahedral, octahedral, and cubic holes as well, that you'll have to be able to know how to count. So if we give you a structure like this to evaluate, we're not going to expect you to know which compounds form which structure, but if we tell you something about the structure of the compound, you should be able to predict its formula and vice versa. Okay? Any questions on this? All right, number 33. How many kilojoules of heat are required to heat 135 milliliters of water from 25 Celsius to its boiling point, and then to vaporize the entire sample? So we're giving you the delta H of vaporization as 40.6 kilojoules per mole. So this is one of those heating problems where we have 2 different processes to consider. We're warming up a substance within the same phase of matter, and that just is going to be Q equals mc delta T like we've used before. And then we also have phase changes where we're going to use the enthalpy of vaporization or the enthalpy of fusion or the enthalpy of sublimation to figure out how much heat is involved with those phase changes. So in this case, we have 2 phases. We're heating the liquid up from 25 Celsius to the boiling point, and then we're just vaporizing all of it. So and then the total heat is just going to be the sum of the heat involved with both of these processes. And here we go again with the disruptive next class. Okay, so phase 1 is heating it from 25 Celsius to the boiling point, which is 100 Celsius for water. There's one boiling point you should know by heart, and that's water, which is 100 degrees. Okay, so that's the first phase. So Q is going to be MC delta T. So we have 135 milliliters of water. As we've seen many times when we're dealing with water, the density is 1, so that's equal to 135 grams. The heat capacity of water is the one you should know, 4.18. And then delta T, we're going from 25 to 100, so that's a change in temperature of 75 Celsius. So that's our delta T. So for this first part here, we get 42,363 joules. We're asking you for the number of kilojoules that are required, so we're going to convert that to kilojoules before we add it on. So that's 42.36 kilojoules with 2 decimal places. Okay, so that's how much heat is required to raise the temperature of the water from 25 to 100. And then the second phase is just vaporization. So for vaporization, the heat is equal to the number of moles of water times the enthalpy of vaporization. So most often these phase change enthalpies, fusion, vaporization, sublimation, are per mole of substance. We have to take the number of moles of substance and multiply it by that number. All right, so we have to find moles of water, which again is just mass to moles. We have 135 grams of water, and then 1 mole is 18 grams. So we get 7.49 moles. Okay, so to find the amount of heat that's required to vaporize this, we have 7.49 moles. And the vaporization enthalpy is 40.6 kilojoules per mole, which is going to give us 304.16 kilojoules if we keep 2 decimal places. And then finally, the total heat that's required is just the sum of these two, so it's going to be 42.36 kilojoules. Most of the heat comes from vaporization, 304.16, and we get 346.52 kilojoules. Okay, so those are the two types of heats we have to be able to calculate for physical processes, warming and warming, cooling, or phase changes. Both of those could come into play in these types of problems. Questions on either of those concepts? All right, and then finally the last one is a phase diagram problem. Which of the following are correct for this phase diagram? Okay, so we have, again, four scenarios here. Okay, so the first one, at 200 Kelvin and 1.2 atmospheres, only liquid is present. So what's helpful to do with these diagrams is keep in mind where the different phases of matter exist. So the leftmost portion is liquid, the bottom right is gas, and then, the solid, bottom right is gas, and then the middle part is liquid. I always mix those up when I say them, even if I don't write them wrong. Okay, so there we go, solid, liquid, gas. Those are the regions of our phase diagram. 200 Kelvin and 1.2 atmospheres. So we find that position on our phase diagram, and that's right here. So for choice 1, we're clearly in the liquid part of the diagram, so that one's going to be true. Let's put a check by it. Number 2, liquid can exist below 0.6 atmospheres. Okay, so if we find 0.6 atmospheres in our diagram, that's this line here, and we see that the entire liquid region here is above this 0.6 atmospheres line. So when you're below the pressure of the triple point, you no longer have the liquid presence. Remember, this point here in the diagram, which is where all three intersect, that's called the triple point. If you're below that in pressure, you no longer have liquid phase possible. So that one's going to be false because liquid cannot exist below that pressure. And moving from point C to D, the phase will change from liquid to solid. Okay, so C here is in the liquid part of the diagram. We move down to D, and that's in the gas phase portion of the diagram. So that's also going to be false. This would be vaporizing the sample if we go from C to D. And then finally, point E is called the triple point. So point E is up here. If you have it in front of you, you can probably see it better than you can on the board. Point E is that point here. The end of the liquid gas line is called the critical point, not the triple point. So that one's also wrong. So the only true statement, the only correct statement is number 1, which would be choice C. All right, that takes us to the end. It's been a pleasure, so don't be a stranger during the next week or in the future. And I hope to see you around in future semesters as well. Okay? Have a good one.
How is number 3 incorrect? From C to D is in. Oh, no. Sorry. Liquid for gas.
That'd be liquid to gas.
Okay, sure. Thank you, by the way. Been a great chemical class.
All right, good.
Sure. I wish I'd had you in Chem 2 or something. Well, I know a lot of teachers Chem 2.
Yeah.
But thank you.
Yep.